Morning. All right, good morning. Online, are you guys able to hear me okay? I apologize, I was not able to get up the notes till right before class. So if you have your laptop or electronic device and want to look at those notes, feel free to download them. They are on the handouts and lectures. All right, so our next section of material is to look at what's called the Laplace transform method. So first off, I want to describe why are we even looking at this method. Here is a RLC circuit that has a DC source. So DC meaning that no AC component, so 1.6 volts. When you close the switch, remember that is that U of T signal, which is just a step function, meaning that after 0, it goes up and then stays up. So basically it's U of T would be the description of V naught U of T. And this was the method we just learned where you find alpha, omega naught, and go through that process. In this case, it was critically damped. And then I went through the solution to find V of C. And then to find V of C from that, you would need to take I of C is C dV dt. And so I took the derivative of that one. And that yielded this I of t, IL of t was what I was looking for. And that is the same as I of c because it's in the same branch. And that yields the 4t e to the minus 5t for t greater than 0. So this was the method we just learned. And I wanted to also say that you could actually find IL of t directly without having to go through the derivative. The way you do that is you still have the view, because it's in series, of the RTH across the C capacitor. And so you find alpha omega naught the same way. The difference is that you substitute all of the variables. So VC of 0 is going to go to IL of 0. VC at infinity is going to go to IL at infinity. And IC0 is going to be VC of 0. And then the I over C is actually going to be I over L. And so just swapping those variables, we can go through the same procedure, find IL of 0, IL at infinity, VC of 0, and then the B1 and B2 the same way, and then you yield the same result. So that's a little bit quicker way of finding that without having to take that derivative. And so you can use that method also to find those. What happens though if we have more than just two elements, 1L, 1C? We can't use this method, right? Because this was a derivation with just a second order partial differentiation. Other question is, what happens if we have now, instead of a DC source, we have a more complicated input signal? So we have a sinusoid, or we have an exponent, or we have, sometimes it's on, sometimes it's off. So that's where we want to look at the different methods of solution. And these are all of the types of methods of solution. So in 1240, you learned about the phasor domain, where you solve the circuit by transforming it from the time domain into the phasor domain. And then once you solved that circuit, you found that it was easier to multiply, divide with the polar form. And then when you had add and subtract, you took rectangular form. And so that was much easier to manipulate those equations to be able to get a solution. And then you transformed it back into the time domain. The limit of that was that you could only do it with a sinusoid, because the sinusoid, we moved into the phasor domain. Remember, it became e raised to the theta t. And so that's the way that that one worked, is that it was transformed into that. So that is limited to only having an input of a sinusoid. The other one is called phasor domain and a Fourier series. And so that would be able to be for any input that was a periodic signal. And what it yields is only a steady state, meaning the end value. So it doesn't tell you that transition from the beginning to that final state. It only gives you really that final state value, which is fine, because a lot of times you don't care what the transient portion of that signal, does it come up as a overshoot or undershoot, or is it critically damped, underdamped, overdamped? So sometimes that doesn't matter. And so that method makes it like, okay, I could just use that method to find at the steady state, what is my value going to be? But then there are situations where you want to know what that information of how it's transitioning. And that's why we went through the last unit, was to understand how does this transition. And so the other way is this Laplace transform. So this is what we're going to look at now, is this Laplace transform. So the Laplace transform, sorry, can have any input signal. It gives you both that transient and it gives you the steady state. So now we'll be able to know, okay, initial value, end value, and how does it transition between those values. So we did go through this with the derivation before, but we only did it for a second order, and it was limited only to those second order, meaning you could only have one capacitor, one inductor in each of those. So now we can look at this, and this would actually have, now we can look at more components than just one L and one C. And so this makes it now like, okay, this is a method that is more robust, and we can do it for pretty much any signals. And so very useful. So the way this is going to work is very similar to how you guys did the phasor domain, where you're going to have an input signal in the time domain, and you're going to translate it into the S domain. From there, we're going to find that all of the manipulations are algebraic instead of differential or integration. So in the time domain, they are always usually that differentiation or an integration because of the characteristics of the capacitor and the inductor. But once we change those into the S domain, you can make it so much easier because we can just add and subtract them. So much easier, or multiply and divide. So that makes it very useful. And then we're going to get to a solution for a variable in the S domain, and then we're going to translate it back into the time domain. So this is going to be our method. So I wrote that out a little bit here, transform circuit to S domain. You can apply then KVL, KCL, node voltage, whatever method you want to solve for those sets of equations. And then you're going to solve for whatever unknown variable. So this also is much easier to find any current or voltage in the whole circuit in a much simpler way. And then we're going to transform back to the time domain, and that's going to be our full signal. So let's look at this circuit here again that I already solved for you, because I want to show you how the comparison is from all the steps that it was before to the steps in this method. So the first step here is to transform it into the S domain. So so how do we transform this into the S domain? So, sorry, pulling up my notes. There we go. So an input signal, let me fast forward a little bit. So the Laplace transform looks like this. So for any function f of t, you're going to define it with a capital F, and that denotes that we're in the Laplace domain, so the S domain. So it becomes a capital F of S. And what that is an integration from 0 minus, meaning right before if you have a switch or in the signal, to infinity. And it's f of t e raised to the minus st dt. So that is the Laplace transform function. We then have the inverse Laplace transform. And so that's going to be the capital F of S, and then the L to the minus 1 is denoting that it's the inverse of that. And so that gets us back to the time domain. And that is 1 over 2 pi j, and integrate from sigma minus j infinity to sigma plus j infinity of that signal, whatever variable you're trying to find that's solved in that S domain, f of s, e to the st ds. So this is how we're going to go back and forth. There are a lot of properties of the Laplace domain. And so, okay, so just kind of quickly, so say you have a step function defined by this AU t minus t, t minus capital T. So what you would do is plug that in for the f1 of t. Okay, now I can't write. So plug that into the f1 of t and then e to the minus st. And then you're going to take it from 0 minus to infinity. I'll go into that 0 minus in a second. It's easier to see in an example why it's there. And then au to the t minus capital T. And so, okay, now it does it. There we go. And so as you integrate this, the a comes out, and then e to the minus st becomes a over s, e to the minus st from t to infinity. And so that's just shifting the variable from 0 to t is going to be 0, so you only bring down the t. So this is defined then as a over s, e to the minus st. So there we go. So for u of t, that translates into becoming 1 over s in the time domain. And then, let's see, you can do the same method to find, so delta t is kind of a weird function. And what that means is it's an impulse. So a lot of times in our circuits, you're going to have a trigger event, meaning like one time something else will reach a certain level and trigger like, okay, now I want to do this because that trigger has been set. We model that by an impulse function. And so this is where that delta t comes from. And so graphically, it just looks like this. At some time frame, I have a trigger event. And so we define it to look like this. It's just an impulse at a specific time. That translated into the time domain, or from the time domain to the S domain just is 1. So it's kind of nice, very easy. And you can go through these and see that each one of these is going to transfer into the S domain as a specific function. So cosine omega t of u of t is the s over s squared plus omega squared. And then you can find the time scaling. So if you multiply an a, so you have a of t, then that scales as 1 over a, f as s over a. And the book goes through each one of these in detail. So if you have any questions like where did they come from, we're going to look at more applying all of these. So just know that they're in the book, and then we're going to use more the table of these. So for multiplication by constant, it's just a multiplication in the S domain. If you have two functions that you're adding, they just translate into the S domain as K1 F1 of S plus K2 F2 of S. That time scaling, time shift, frequency shift, the first derivative, the second derivative, the time integral, the frequency derivative, and the frequency integral. So these are going to be the ones we're going to use all the time. So I don't require you to have to derive these by each time because these are going to be frequently used. It's just know what they are as far as the translation, but know where they came from. The f of, so like the first derivative where it says f of 0. Okay, it's not working. Okay, back to here. So for instance, with this one that's like f of 0 minus. So this will be the function for whatever variable you're trying to find right before like a switch is occurring, or if it's a signal that changes at 0. then you would find it right before that signal changes. So that's the variable that you're trying to find in the S domain. So that's what that 0 minus means, is that you are looking at that initial condition for it. So that's more of an initial condition of for your variable. All right, so we're going to use this table of properties. And then, as I said, the other ones are, there's another table that has all of the functions themselves, already translated for you. So these are called Laplace transform pairs. And so you can go back and forth between them. So we're going to use these two tables to now go back and translate the, well, I'll back up. So if I wasn't to use the Laplace, and I was going to just solve for this, I would have the voltage across this, the voltage across this one. This is going to be a function, and say this is now no more, which I'm not going to use yet. I'm going to just call this some function of V naught. So if this is now a function, how would we solve this? So we're going to go through the same, there's one branch here. I'm going to look at it when it's already closed. And so I'm going to just take a loop. So I have a plus, minus, minus, minus. So minus I times R minus VC minus VL equals 0. And we know VL is I L di dt. And if we're trying to solve for, say, IL in here. So previously we solved for IL, so comparatively, we're going to use IL as our variable of unknown. So we need to get all the variables in here to be in IL. So VC, we also need to get into IL. So we notice that IL equals IC. And we have the equation for IC, which equals IL, to be C dV CDT, but we have it in terms of VC, so we would have to integrate both sides of this. And so doing a separation of variables, we can do IL and bring over the DT and the C. And then integrating, remember the Laplace is from 0 minus to infinity. So need to back up one sec. So in order to do that, this is going to be from minus infinity to infinity. And then if we change the variables on that, it's going to be 0 minus to infinity. How do I say this better? I'll just leave it at that for now. Okay, and then taking this from minus infinity to infinity. So plugging this in, we have minus or plus V 0. I'm going to change this to IL. And now, sorry, this becomes VC from minus infinity to infinity. But then if we do it from 0 minus, it's going to be VC minus VC right. Okay, and then let's see, minus VC. So this becomes the integration from 0 minus to infinity of 1 over C IL dt. And then a plus VC 0 minus, and then the minus L DIL dt. So now from here, we can translate this into the S domain. So IL is our function we're trying to find in the S domain. So that just translates over to the capital IL of S. So V naught becomes whatever function in S. And then IL just becomes the capital IL of S times R. And then we're going to use the property of integration. Which is 1 over S, F of S. So we have the constant of 1 over C. And then the capital I of S over S. And then VC of 0 minus is a constant, so that becomes a constant. And again, it's just over S. And L and the differentiation. So S, F of S minus the function at 0 minus. So that becomes L of S, I of S minus I of 0 minus. Should say IL of 0 minus. So before the switch moves, we have to look at those initial conditions. And it's open, and so IL of 0 will be 0 and the capacitance will be 0, right? I can redraw that. So the switch is open. Inductor becomes a wire and this becomes an open. So there's no current going to be here and VC will be 0. So those will be our initial conditions. And so this reduces down to, I'm going to remove the S portion. So just a capital V naught. And then this becomes 0. This one becomes 0. Forgot the 0 over there. Minus ILS. So now this is much easier to find. Sorry, these are ILs. IL here. So IL is going to be V naught over R plus 1 over CS plus LS. And we can go back and plug in the numbers 4 for R, C for 0.1, L for 0.4. And translating so say we are looking at 1.6, that's just going to be a number. And so V naught of S is going to be 1.6 over S. And so looking at that one particular function, then this becomes 1.6 over S times 4 plus 1 over 0.1 S plus 0.4 S. And multiplying those out, you get 4 over S squared plus 10S plus 25. And that ends up being S plus 5 squared. So this is the IL of S. So now we need to just go back to the time domain. So we're going to look at this. So it's an S plus 5 squared. So we go look at the table. And looking at that, we have this function here, 1 over S plus A squared translates to TE to the minus AT of U of T. So we can use this relationship or the Laplace transforms. And so IL of T, what happens with the 4? Yep. Correct. So you just take that 4 and it is multiplied by the Laplace transform of the other portion. So it's going to be 4 and then T, E, and A in this case is what? So you do a minus 5T. And then that U of T just means that it's, for T greater than 0. So you can leave it in the form of U of T, or this is how we've been writing it before. So we see that this is exactly the same as we did before. So the next question is there an easier way than having to write out all these derivatives? And yes, there is. So I wanted to show you this because, you need to understand where these components come from. As you look here, what do you notice? You notice that the R translated over right to an R. For the L component, that translated over as LS times I of L minus the IL of 0 minus. So that initial condition. And for the capacitor, it was VC of 0 minus over S. So these are the translations of the components. So R goes over to an R. For the inductor, you have VL is equal to L DIL dt. And so if you look at the IL portion, it's going to be 1 over L and the integration from 0 minus to T of VL of dt plus IL of 0 minus. So writing these, if you write it in the form of a voltage, VL, it's going to be SL will be the inductor translation. And then it looks like it is just an impedance. So just like we did with phasors, it translates over to LS, but now we have the initial condition of a minus L, IL 0 minus. So because it's a minus, it would be oriented in this direction, a minus to a plus. And then if we wanted to write it in terms of IL, we could write it as this. So IL is VL over SL plus IL 0 minus over S. So whichever form you want to put it in, both of those are valid. For the capacitor, same thing. It would be I of C over SC, or there would be a current source in parallel with it. So let me, if you don't remember these, you can rederive them each time. Let's see. Integration. By using the properties. So you know the relationships. So this is what you've had memorized, are these two. So taking the integration of both sides of these, you first need to do a separation of variables. So you do the dt over to this side. Actually 1 over L over there too. And then these are from minus infinity to infinity. But we need to get this one in terms of the 0 minus. And so to change those over to 0 minus, you have to integrate. So this is going to be the IL. I say this, I'm not saying this very well, but you have to take the initial condition. So then this becomes IL of 0 minus to infinity of VL dt. And then you add the IL of 0 minus over to the other side. So that's where the IL equation comes from. And then when you translate that to the S domain, you're going to use this property for the differentiation for the VL. So it becomes S L IL minus, and L is multiplied by each of them. And so L IL 0 minus. So that's from the differentiation property. And then from the integration, we have VL, the integration becomes VL over S, and then IL 0 minus over S. You guys follow that? Is there any questions? Yes.
This is when they're in parallel series, right? These are the two cases. Like the two.
So this is to translate them from the time domain into the S domain. You can use either of those, which are the same. It just depends on which structure you want in order to solve the circuit easier. So if it's going to be a parallel form, it's going to seem easier to solve, you would choose that one. So you need to know, like, okay, if I just remember the function itself and I don't remember how, I don't want to memorize these, how do you get there? So I just want to make sure you guys do understand where each of these is coming from so you can translate them over. All right, other questions? Okay, so same thing with the capacitor. That would be the same method. If you have the memorized equation and then do the separation of variables to be able to get the form of VC. And then you're going to change that over into the S domain. Right, so we're going to use this now. Yes, question. Yeah. So that's the next step, is we're going to use this method now to go back and solve that same problem we just did. So it was in, it's in series here. So I think it would be easier to use the form where it is the voltage. So I'm going to use, I already moved them down here. I'm going to use the, I already moved it over. So the one where they're in series together. And you're just going to replace now the capacitor and the inductor with those. But in order to do this, we need to know those initial values. So the initial value again goes back to the same circuit, which we already solved for these. So we know in this case that VC of 0 is 0 and IL of 0 is 0. Or IC of 0 or VC of 0 is 0, IL of 0 is 0. So that makes this a little simpler model because these both go to 0, which if they're a voltage source, they're just a wire. So these are just going to be wires. And now we treat each of these like just a resistance kind of impedance. So now as we go around and take the loop, and here again, we change, call this V naught. We change over the voltage to whatever the S domain voltage will look like. So as I said before, the 1.6 becomes 1.6 over S. So and the S was from what? I should go back. Let me go back to this. It's because of why? Yes, because it's U of T in there. So the 1 over S is from that U of T. I forgot to mention that. So if we're looking at the same, and we have V naught is 1.6 U of T, then that translates over to V of S as 1.6 over S. And the values of this becomes 1 over 0.1 S, and this is 0.4 S. So as I take my loop, I'm going to do the second sign. So I have a plus, minus, minus, minus. So plus V naught, capital, minus I of 4, minus I of 1 over 0.1 S, minus I of 0.4 S. And solving for I, four plus and then the V naught is 1.6 over S. And this ends up being the same. So we have 4 over S squared plus 10S plus 25, which is 4 over S plus 5 squared. And we do the same thing, translate it back. And we get I of T, this was L, of 4t to the minus 5t. And you could use it as u of t or whichever way you like to write that. And that's exactly the same. So that was using that Laplace transform pair again. Much easier, right? Than having to go through all the derivatives and the integration to just change over these values. Hopefully, hopefully it looks easier. I'm getting some blank looks like, are you kidding? Yes, questions?
Can you explain what the 1.6 over S, so that 4 over S squared and S is
Uh-huh.
Yeah, I mean, lost. So I understand that you choose the S out, right? Then what do you multiply it to like 4? Like it's a nice easy factor.
Yep, I can do that. Okay. Or so I multiply first the S into parentheses. So it'd be 4S 1 over 0.1. And then I want to get an S squared by itself. So I'm going to pull out the 0.4 that's in front of the S squared. So when I pull it out from the S squared portion, I need to divide this one by 0.4. 1 over 0.1 is 10. So that becomes 10 over 0.4. And 1.6 over 0.4, just make sure it is 6 over 0.4, I think it's 4. So 1.6 over 0.4 becomes a 4. And then this is S squared, 4 over 0.4 becomes 10. And 10 over is 25. Okay, yeah, so yeah, thanks for slowing me down for that one. Yes, so you want to make sure that you're trying to get the form in these is to match them up with something in the table itself. So that's why I was trying to get it down to a factorable form. Yes, Katie.
I don't have a specific question, but,
Okay, so let's go back and go through the steps that we just went through. Okay, so the goal is that we want to use this now new Laplace transform to solve the circuit. So that's the goal of what we're trying to get to. So how do you use this method? And so I first showed like, okay, there's properties that the Laplace has. So what we're going to see is we need to translate from the time domain to the Laplace domain. So understanding that the properties, so you can translate them into the S domain. So that was where I backed up on that. I went through all the derivations of from just knowing IC is equal to C dV dt, and then the L, and showed how they move into the time, from the time domain into the S domain. So what you guys need to know is from here, how do you use this information now? So what did I do here for the first step? So what was the first step here?
Transform your circuit to
Okay, so transform into the S domain. to do that, you pick which form do you want? Do you want the form of the inductor with a voltage source or the inductor with a current source? So that just looks at the circuit and decides which one is going to be the easier form. If they're all in series, having the inductor with the voltage source is going to be easier to solve. Yes.
Is there ever gonna be a case where you're gonna wanna have your capacitor be in parallel and then your inductor be in series? Vice versa?
So when you're in a parallel form, sometimes that parallel with the current source may be an easier form to solve.
Like just like all is constantly the same, like say like if you say you're doing the inductor, right, you have a voltage source. And you chose that series version. Would you ever use like a capacitor with where it's like in the series version with the current source?
Yeah, I mean, it just, again, depends on your external circuit and what seems to be the easiest form for you to solve from there. And it makes it much easier if your initial conditions are 0 for either one. Because then it just reduces down to the SL for the inductor and then the 1/CS for the capacitor. All right, so you have to, yes, question?
So I was just gonna ask about the S domain. So when you say like VC equals like all that stuff as an equation of S, does that mean that we can still use like all of like the voltage laws and Ohm's laws in the S domain too?
Yep.
Okay.
Yep, so Ohm's law is just gonna be, you're gonna treat the value of the impedance for the inductor as SL. And so instead of being 4, it would be SL times, and that would be your impedance times the current is gonna equal the voltage.
Okay, so even if we have 4 components, we can just simplify these.
Yep.
Okay.
So now we can do more than just the 2 components in there. We can do a 5th derivative without having to go through the whole derivation in that differentiation. That's going to be a nightmare. I don't want to solve a 5th order differential equation. So that's why we're doing this, is because now we can have an unlimited amount of capacitors or inductors in there. We know that each one is going to contribute a time domain S in there because of the form that it goes. So if we have 5 in there, we're going to have a 5th order partial differential equation to have to solve, which is not going to be fun to do in the time domain. So that's why we are going this method, because we can solve any circuit this way, model it by these elements we know, and treat it like an impedance, which is just going to be so much easier. That makes sense? Okay. Yes.
So when we transform into the S domain,
Yep.
let's say we have like multiple inductors. Can we combine them like an inductor, or we combine them more like a resistor?
So once you're in the S domain, you treat them like an impedance. So it would be like the resistors. So if they were in series, you would add them together. And if they were in parallel, you would have the parallel form. So good thing to say. I'll put that as a note. So combining them in the S domain is treat it like a resistor.
So that's something we just take, we just add them together.
You could just add them all together. Yep. So here you can see how they would have just added all together. And so we could have already just combined them all together and just done V over R for the current, which is what this is. It's V over the summation of those. Yes.
So say we were to replace those outputs right there instead of with the voltage,
Uh-huh.
like use this the parallel.
Yeah, so his question is, what if I had done the parallel connection here instead? Whoa, that was not what I meant to do. So if that was the case, the circuit would have looked. Get a little smaller. So it would have just looked just like this if you wanted to do the parallel instead. So you close the switch and then these would be the connections that you would have. So you could then go and solve this circuit for the current, but as you can see, by adding in those extra current sources, that seems to complicate this circuit. So instead of doing a simple just loop, I mean, I could still do the loop, but then it complicates it to have those currents in there. So the current going through this branch is not going to be IL anymore. So you would have an unknown variable, an unknown I there and an unknown I here. And so as you take that loop, you have two more unknown variables there as you go around. I mean, you could still solve it, but it kind of complicates it. So that's why I kind of already knew the other circuit form, the other configuration was going to be better in this case with series. Does that make sense? So in this case, with initial conditions of 0, this becomes simpler because then this component goes to 0. And then this component goes to 0. But as you've seen, like when we solved some of the other circuits previously, they weren't always, those initial conditions weren't always 0. Yeah. So then in that case, those aren't just opening up and you want to be cognizant of which one you're using. Okay, so back to the steps. So transform into the S domain, and with that S domain, you needed to know two components here, the initial conditions. So you have to solve for the initial conditions of VC of 0 or IL of 0. Yes. Not yet, but yes, I will later. So yes, there'll be quite a few problems. And you can also go and do test your knowledge on the, it's chapter 12, by the way. And yes, I forgot to answer that online. So chapter 12 is the content we're going through right now. So you can go test your knowledge on chapter 12 and it will give you some extra problems to go through of solving the full problem like this, or it will just ask you to, like, what does the circuit look like when you change to the S domain? So some of those that are a little bit simpler too. But those would give you some extra problems to practice. All right, so transform into the S domain, we get a circuit like this. Then what do we do?
Solve for like
Correct. So then you're going to create your set of equations. So use KVL, KCL, node voltage method, Ohm's law. And when you have a more complicated circuit, you know, you can have, if you have 5 unknown variables you're trying to solve, you can again get 5 equations, set them up in matrix form, solve them as an S domain solution, and then use that equation to translate back into the time domain. So you can do a very complicated circuit solution in the S domain also. So you need as many equations as unknowns that you have. So far, we've only been solving for one variable, but I do want to mention, you can do this for a very complicated set of equations. After you get this is going to give you a solution for a variable in the S domain. So then what do? Taylor?
Solve for your unknown variables.
Yep. So solve for unknown. So in our case, we got like IL of S. So after you get the variable that you're looking for, what will you do next? Do what? Heard somebody say it. Yep.
Transform back to the time.
Yep. So Katie, did this help? Okay, so now the thing is, okay, I got to do lots of practice, right? So that's what you're going to work on next is a lot of practice. And enough practice so that you're like, okay, which configuration do I want to pick here to make the circuit not more complicated? And that's going to be more practice of different problems. So let's look at this one. Okay, first step. Okay, so we need to do what? Transform into the S domain. So this is our input signal. Anybody know how to write that input signal in a mathematical form? Say it louder, sorry.
U of t times U of t minus 1.
So it wouldn't be multiplied. Yep, it would be a minus. And when you have U of t, it's just to 1, and this goes to 6. So what would I do? Yep. So it'd be 6u of t minus 6u of t minus 1. So that is the mathematical description of that signal right there. So this is is of t is equal to that. All right, so what next? So first we need to write it in time domain. What is the input signal?
Would you replace the components or the inductor class with the parallel?
So yeah, I think that would be an easier one in this case to do the parallel forms because then I have just, all of them are in parallel. And then I could use node voltage and it's just a node voltage out of each of those branches. So that would be my choice too. So I'm gonna go back up and copy those. They're a little small, but goes in there. All right, so
The current be pointing
same direction in all the substitutions. Like, because I see the capacitor and inductor pointing opposite.
Yep, so that it was dependent on the forms that they had. So here I had
And on the current,
so the IL, when it translates over from that integration, it was 1/L, and then it was the plus IL of 0 minus over S. But in this one, it was, oh, that's not what I meant to do. It was, so in this one where you had IC, that was taken from this, where it's CS VC minus the CVC 0 minus, because it's a differentiation instead of the integration. So in that case, you had a minus in between there. So as I do a summation here, IL goes in, and then VL over SL was a plus, and then a plus IL 0 minus over S means that it has to go down for the first one. And then for the minus one on the bottom, it would have to go in to give you the minus. Does that make sense? So they are different. And it is because they're based off of the equations themselves. So for this one, for IC, it's a differentiation, which means you have that minus initial condition. Does that help?
yeah, it helps.
Okay, so they are going to be different. Okay, so what are we going to have here? How do I translate this signal into the S domain?
With the 6 over X minus 6 minus S over S. Based off of the table.
Yeah, it's 6e to the minus S over,
S.
yep, correct. So you use the table, and that translates over to this form. So this is going to be your I of S. And then we have, oh, I forgot to, what were the values for L and C? Oh, I didn't have values for L and C. Okay, so we're going to do this in variable form. So assume we know our L and C values. So those would be our known values. But we're going to keep them in variable form. And then what did I want to solve for? I want to solve for IC of T for this. So what else do I need to know here in order to solve this? I have IS, R, LS, 1 over CS. What are these values? Yeah, Taylor, did you have a question?
Oh, you're asking what values I need of this?
Okay. Yep. So how do we find these values?
Set like, so we have 0 minus.
Yep. And 0 minus in this case would be when the input is at 0. So for finding those initial values, so you look at the input signal and look at it right before it changes at 0. So in this case, that input would be 0. And so if that's 0, what does the circuit look like? So this will be 0. Back to these. All right, so 0 amps here, which means what are these values going to be? Both 0, correct. So we have a 0 here and the voltage is 0. So that makes this circuit easier. If both those are 0, I see. What do I notice about that circuit here? Yep. So you could combine them. Being in complex domain, that makes it a little harder because you have the 1/SC. And so I tend to just like node voltage, as you've seen. So I would just do node voltage here. And so if I did it from the top, I would have this top one would be all the same node. And I would have a minus IS going in. I can call it VX if I, or, note that VX is the same. VL and VC. So all of those are the same because they're all in parallel. So VX over R would be this branch. What about this one? So somebody said RS. R just transforms over into R. So it's just a multiplier number. So when you multiply it over, it just is R times the I of S. All right, so then this one. Correct. So it's VX over 1/SC, which then goes to the top. So you could say this is VX over 1/SC if you want. So now I can combine all of the VXs. And we got a value of VX of S. And so if I want to find IC, what will that be? And so, I'll write this down here. So now I need to put in the IS, and I also want to get this form into just an S squared by itself. So how do I manipulate this mathematically to get just an S squared instead of the CS 1 over SL? Okay, so if I multiply the top and the bottom by S, now what?
You can factor out a C out of the denominator.
Correct. So note that you have the C still with the S squared. So you want to bring that out. So it becomes S squared plus so for every component that doesn't have that C, you need to divide the other ones by that. So you should be able to see that these are the same. So as I multiply that C in there, that becomes CS squared, which is this term. The second term is S over R, which is this term. And then the last one is 1 over L, because the C's cancel. So then this cancels out these C's here. So I'm left with S squared IS over S squared plus S over RC plus 1 over LC. And now I'm going to look at plugging in that IS. So we're going to have S squared over all of this again. And now it's multiplied by 6 over S minus 6E minus S over S. So from here, we want to get this into the forms of the table. And you can see here that there's going to be two forms. There's going to be the first term times S over S, 6 over S, sorry. And the second term, which is that multiplied by 6e to the minus S over S. So we are out of time for today. So use this as an exercise to try to solve this. And next time we'll go through the rest of this. Okay. All right, any questions? Yes.
So you have S squared, so it's S squared over the S, whatever. Define value of X to be that exact same as an S squared integration, some S plus A. Right?
Yeah. So you could do something like that.
Okay.
So you would want to try to get it down to S over S squared plus omega naught.
Can you take like individual like S elements, transform them back and then just multiply them together? Or you have to take it as one of the forms?
You have to find it in one of these forms and then translate it back. All right, see you guys. Sorry, did you have a question? Elijah, did you have a question?